Yo, what's up, everybody? Welcome back. Today we are continuing on with the attempt to write a neural network that classifies, I think classifies may be the wrong word, but it's like the easiest one to use, the direction that a barcode is facing. So I've kind of been part of this larger project to write any barcode detector to run on my website so that I can, like, as I am taking food and putting it in my fridge, scan it so that I know kind of hand wavy how much of everything I have. That will allow me to do things like auto-generate grocery lists. It will allow me to filter recipes by ingredients that I have in the fridge. It'll allow me to... that's probably it, but it would be hype. It'd be kind of fun. And we found that, doing like the most simple thing that you could do, you might run into some problems in the real world, right? Sometimes there's motion blur that makes it pretty hard to like detect the actual segments of a barcode, right? You can see them with your eyes, but like algorithmically, this is getting like on the edge of what I think is like reasonable to expect my thing to be able to parse. There are things like this where big chunks of the bars get like occluded by like the corrugation of the cardboard. And I'm sure that like this one's probably parsable, but like it's probably easier to parse with, leveraging information that you know about like bars and like how they are supposed to look. Sometimes the background is not even black, it's like reflective and shiny, and like sometimes they're like curved and like, there's like bright spots that occlude parts of the bars. All of this stuff makes it so that like the simple just scan one line, do some like basic signal processing isn't good enough. I'm sure you could do this with hand roll techniques, but we're too stupid. And so what are we doing instead? We're building a neural network framework from scratch so that we can show it examples of barcodes and have it train on those. We have kind of like the first thing that would probably be easy to do here is if we could predict the orientation of some stripy lines, that would be pretty hype. So we have some data here where we have, a thing and the arrow that's coming out of it is like its orientation. We want to train a neural network to predict this same thing, which should be pretty straightforward, right? If I were to do this by hand, I would run a gradient, a horizontal gradient detector and a vertical gradient, I guess like convolution. You could basically run like a little box of numbers over this thing and get it to predict, or not predict, like tell you what is the change in horizontal pixel at this pixel and change in vertical pixel. You like add all those up and normalize them and you probably get something that's like approximately correct, right? But this is like a good kind of test case for a convolutional neural network, which should be able to do the same thing with very, very little, like few weights. And so we kind of started on this yesterday. We implemented convolutions for our neural network training framework. We have the forwards pass implemented, pretty sure it's right. And as after you do the forwards pass, you like compute, hey, how wrong was I? And for how wrong I was, how does each of the numbers that I use to get to the final answer, how do they like contribute to the global incorrectness, right? And to do that, you kind of like walk backwards through the computation graph. You say like, hey, I multiplied these two numbers and these two numbers and these two numbers and then added all those together to multiply them by another number. And like all of these like contribute to the final answer by like some ratio of those multiplications, essentially. And so we weren't really sure that our backwards pass was correct because it's actually like pretty tricky. These convolutions, oopsies, I didn't want to move that. What they are is, imagine you have an image, right? We'll say that it's an image that has like 3 channels, right? There's like red, green, and blue kind of all stacked up in the same image. And say you have like 1,000 of these, right? Because we're on GPU, we can do a lot of processing at once. And so we want to like run a little box, like maybe like a 3x3 box over this entire image. You say for every pixel in this image, look at this, put this 3x3 box over it and multiply the surrounding pixels by that one, right? You can imagine that a blur would be like if you filled this box with all ones, it would like take all of the surrounding pixels and like mush them together and make the thing blurry. Now, but however, the box you're running is actually also 3D, right? Because he might want to do things like say, let me look at the red pixels, the green pixels, and the blue pixels. If there are a lot of red and green pixels, maybe I want to do something, but not if there's a lot of blue pixels, right? Maybe you want to do something like that. And then, as your output here, you actually get, if you ran one box over this thing, you would get one output. But you might want, like, for neural network training, for there to be, like, maybe 64 outputs. So you have 64 of these cubes that you run over in parallel, right? And you get like 64 channels out. And then you do it again and again and again. And eventually you like get to like higher and higher level concepts, right? Like you could imagine your first pass would be like, hey, am I like what is my horizontal change in pixel value? And then from there you could be like, okay, if I have both horizontal and vertical, that's something. And then you could like sharpen the image and blur the image and be like, hey, if the difference of these is something, do something with that, right? There's all sorts of like interesting things you could do there. And so you get like deeper and deeper down here. So this is if you want to say how much does like this cell in this kernel affect the final output, it's actually like kind of hairy. And so let's just look at where we ended up yesterday and see if it makes sense to us still. So we like run some code on the GPU, and here we say we're running. Then again, you could say fuck the lines and read the numbers. I just joined, by the way. That's an interesting idea. That's like a maybe. I think that that's less reliable, but I think that's a maybe. But also I think it's less fun. So here we say something like, so this kernel, we run one GPU thread for every cell in our kernels, right? So if we have like 64 kernels times 3 times 3 times 3, that's like 64 times 27, which is like probably on the order of 1800? 64 times 30-ish? Yeah, something like that. 1 gig LSP log is crazy. Yeah, that is kind of crazy. I should delete that. I think it probably grew a lot when we were doing, we implemented some LSP thing at some point. Oh, for the code map visualizer that we never used. And so that probably blew it up a lot because we were using like debug logs. But anyways, so for each of these cells in the kernel, we go over every image that it affected the output of, right? So here we have like 1,000 images. He looks over each of those 1,000 images, and then he looks at each pixel in each of those images and sums up essentially how much like the pixel value so each pixel has like an incorrectness value on the output, right? So like over here, if we wanted this thing to like, say you like sum this thing and you want the answer to be 1. Oopsies. What the fuck did I just do? You want the answer to be 1. Where am I? Hello? There we go. Oh my god. So you want the answer to be 1.0? You basically say like each pixel in here contributes to that 1.0 by some amount, and then you want to like, for each pixel in the output, you like see how much a change in that kernel would affect all of those pixels. Hand wavy, right? So that's like kind of what we've calculated here. We just don't know if we did this right because the math or like it looks trivial, and it probably is trivial, but my dumbass brain is not like, it's hard for me to work because it's kind of like backwards from the way you normally work, right? You usually loop pixel by pixel and then do a thing. Here we're like, we have 1 pixel and we want to do a thing based off that 1 pixel, and it's like you have to work the whole chain backwards. So anyways, that's where we're at. I think the first thing we need to do is prove that our backpropagation works. So we started by like writing a test yesterday, but we didn't really know how to like get the right answer because again, like this answer is built up from running over like many images, many pixels, and multiplying by all of the incorrectness values in that output image. And it's like confusing, right? And so what we started doing yesterday was we started writing like a PyTorch thing that does the exact same thing, right? So we create some image in here, we run a kernel over it, we run a convolution over that thing, and then here we need to like get a loss value that we can backprop in PyTorch land, and then compare that we get like the same thing. I think that's kind of what I want to do. And so I think that like we can just do something like sum the output of this thing. So we can say like total loss, and I think if you just do like total loss backprop, I think in PyTorch land, I think that should like initialize gradients for everything. I think. So let's just see what happens if we do that. We need PyTorch. But I think that should give us something that we can like compare with in our framework. Are you using an NVIDIA GPU? Nope. AMD. So does this do what I want? Backprop doesn't exist. How do you do backprop in Torch then? PyTorch backprop. How do I just like run backwards propagation? How do I like do this part? Backward. Backward. Okay, and then grad's in this, but we do have grad. Okay, so this is interesting. The gradients of my kernel seems very large. So my kernel here should be 1 by 2 by 3 by 3. This is a 5 by 5 by 1 by 1. So that's confusing. I don't like that. Maybe the gradients are like, hold on, let's look at the like total loss grad. What is this? Read the warning. Yeah, that's a good point. Grad attribute of tensor that is not a leaf tensor is being accessed. Its grad attribute won't be populated. If you need the grad field to be populated, yeah, good point. Use retain grad on the non-leaf tensor. Okay. Okay. That makes sense because I could see why this happens because of the way that we've implemented. Okay, let's look at this again. Kernel grad. Oh, I'm a dumbass. We're printing another thing. I'm just printing two things, and I wasn't seeing the one I wanted. Use retain grad. Do I have to do like this? No. Maybe retain grad like this, return something? No. Let's look it up. Torch, retain grad. What are we supposed to be doing here? Enables the tensor. So it seems like it's doing what I want, no? Maybe I have to do it here? Oh, because we did reassign the kernel here, which is confusing. So we were doing it on the wrong one. There we go. Okay, so this kernel now has gradients that arguably make sense, right? We see they have some sort of structure to them, but I think we now need to prove to ourselves if like our thing does the same. So I think that what we can do is we can say, can we do like out retain grad here, and then print out grads as well? So this is kind of like after the kernel runs, the output of the kernel runs will have some gradients attached to them, and I think that's like kind of analogous to where we want to be, right? So this makes sense. This is like a bunch of ones. He says, my loss contributes to like the final loss by 1.0. Any change to me will change the output by 1 because we just sum them. If everyone checks against PyTorch, what does PyTorch check against? Yeah. I also don't really like this, by the way. I want this to be like non-linear. So we can probably do something like instead of summing here, when we do out.sum for the total loss, what I really want is like the top left cell to contribute to the loss less than the bottom right cell. Like maybe have some sort of like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? In which case, maybe we do like out times, like out equals out times torch arrange. So this will give me like sequential numbers. And we just have to like match the shape of the output, which is 1 by 2 by 5 by 5 or something. So how do we specify the shape here? I think that we reshape after. Torch, arrange. So here we want to like do, you know, from 0 to 25. And then we want to like reshape this to 1 by 5 by 5 or something. That sounds kind of right. Ice Leo, thank you for the 5 gifties. Much appreciated. I will say, if you said earlier you haven't recovered from going down the auto stock trading rabbit hole, if you're like, I haven't recovered, maybe you shouldn't be dumping this much money on me. Maybe. But I appreciate it either way. Okay, so we take this thing and we multiply this by out. I think this is what I want. Something like this. And then we want out retain grad here. Oh no, we want out 2 because we want to preserve the initial output here, and then we use out 2.sum here. Yes. Okay, so now I'm hoping to see, nice, that the gradients for our output are now like of a shape that I like. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now this is like something that should test a little bit more accurately, I think, instead of something super uniform. So now we have all of the numbers. If we just punch these same numbers into our thing, maybe we get the same outputs, right? So let's try that and just see what happens. So I think we had somewhere math executor. So here, let's like just copy the gradients here. So this is like this: 1, 2, 3, 4, 0, 1, 2, 3, 4, etc. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. Let's do this, line things up. And now the moment of truth, what happens when we look at our kernel gradients? So can we do like print I don't really know what these gradients are supposed to look like, but maybe they'll be interesting to us. Wrong thing. Run the tests. This is the last test we run, so we have to build a little suspense and wait. But hopefully, fingers crossed. Okay, so bad news, every single one of these is exactly the same. So this is not what we want to see. Not at all. And so the question becomes, why is that happening? So, yeah, we need to start debugging. So I guess what I want to, maybe it would be nice to try to prove that we understand the math a little bit, right? If we should be able to get to this same answer by hand, hopefully, right? So, so what are we doing here? We have an image that looks like this, and we run this kernel over it, and we want to know how much each of, like, hold on, what are we looking at here? Our output is how much each of these cells in the kernel affects these things, right? So my understanding is that this should be, this top left 0 will touch all of these cells in the kernel, right? Because it will not touch any of the corner ones because it's above and to the left, right? So if we would have to go like out of the image to get to there, right? Okay. So it should be that if we take this set of numbers and multiply that by the gradients here, we should get the same answer. Right? So if we do image from the first image, the first channel, from 0 to 5 in width, 0 to 5 in height, is that right? 0, 1, 2, 3, 4, 5, 6. Maybe to 6 if these aren't inclusive. Let's just see for a second what that looks like. 1, 2, 3, 4, 5, 6. So it looks like it's inclusive. Oh no, wait. Hold on, my brain. Oh, this doesn't run on the bottom row. So it's 0 to 5. Okay, so this is what the top left cell of our kernel sees in this picture. And if we multiply this by out grad, we should see what is essentially like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, but all of the cells that were 0 get like zeroed out. Okay? Hype. So if we just sum this thing, does this give us the same answer as the top right corner of this kernel? 246, 246. So that's a pretty good sign. That means that like we understand the math here and what's supposed to be happening. We're like, if we do it by hand, we get the same thing, right? So that's a pretty good clue that there's just a bug in our calculation that we have to fix. So is it easier somehow if we like really strip down this problem even further? Maybe not. I think that we can get away with, okay. So downstream grads, we know has the right shape. Okay, that's reasonable. So what are our inputs to this kernel gradient thing? It is the downstream gradients, i.e. the 0, 1, 2, 3, 4, 5. We have the input image. Wait, hold on. Oh, yeah, okay. So the input image and our outputs. Okay, cool. So if we go back into like the GPU code that's running for this thing. Which is in conv.cl. Not first try, Zad. Yeah, so true. So which function is this? This is conv many grad kernel. Here we go. So can we do something like, we can probably print out this thing, right? The masked version of the gradients. So we can say if image index is equal to 0, printf x y image x image y maybe. And can we look at the value here maybe? So this is image x, image y, and in image times in grad. Okay. I wish that there was a way to filter the test run in Zig so I don't have to run them all. I guess we could comment them out. Okay. Oh, we probably also want to filter for channel 0, right? Is this my second or third resub during the barcode arc? Okay, you don't have to make us sound stupid like that. That's fucked up. What the fuck? Um, I think you can filter test and zig. Okay, that's good. We should learn how to do that because this is fucking annoying. Okay. So I bet you we're doing some like out of range or something. Oh, we also wanted to look at hold on. We also want to only look at the top left corner, right? Kx equals 0 and ky equals 0. Okay, let's see. Is it like as part of the build? Because when I looked at the test runner, it didn't have much. But maybe it's like here. Test options. Filter. Yeah, so filters here. It's probably here, right? So on build, we go like filters equals conv many grad or something. Probably. Out of range. Rust would have prevented this, by the way. Fuck! I should have used Rust. Okay, so now this thing isn't running at all? Shouldn't kx sometimes be 0 and ky sometimes be 0? Because global ID will sometimes be 0? I guess maybe the input channel is 0 over something? No, that's still fine. Hello? What the fuck? Maybe it only prints on failure? No, because this is printing in OpenCLN. What the fuck? Hi, Mom. I'm confused. You can run with dash dash test filter? Oh, I should have just been doing that then. Okay. So why is this not happening? Let's just do... Can we do this? Actually, let's just do the same if up here. And do something here. Maybe there's like an early continue. Zig might be doing something similar, like capturing stood out. Yeah, it might be. But if I do hi mom like this, we do see it, right? Yeah. So it's like input channel and kx equals 0 and ky equals 0 is never happening, which is very surprising. Because global ID should sometimes be 0, surely, right? Right? Like, am I crazy? Yeah, he's 0 sometimes. So am I crazy? If global ID is equal 0, can we print out global ID kx ky input channel? Like, what the fuck is going on? Am I stupid? I might be. If kx is 0, ky divides by 0? Oh. Yeah, this is supposed to be width. Good eye. That probably explains a lot. That explains a lot, actually, when you put it like that. Oopies. That's what, yeah. There we go. Okay, so some of these values are still fucked. So we're probably doing something fucking stupid. But let's just start at like image x. We wrote image x twice here. Image x, y. So can we go, let's like condense this a little bit. X, y has this. Okay. So 0, 0, 0. Hype. And then why are we saying this like so many times? Because we're not checking image index equals 0 as well. Surely now we should only see... Like, shouldn't this not happen more than once? What is my global ID here? Am I, like, accidentally calculating, like, running this many times? 0, 9, and 18 are all mapping to 0, 0. That doesn't seem good. That doesn't seem good at all. So our kernel size is 3 by 3. And... image index is once. So this is happening... Okay, so what is our inputs here? What are our inputs here? We have a math executor here. We have an input kernel that is 3 by 3 by 2. So the fact that he's ever getting to 18 seems like a fucking problem. Seems like a fucking bug. Right, so like we should be running this. B gradients matches the input kernel dims. So it was 2 kernels. No, it was 1 kernel, right? Hold on. What is our shape here? Math executor. What's up, Gradient Boy? What up, dude? Gradient Boy is crazy. Yes, this is 1 kernel, 2 channels, 3 by 3, right? So B gradient number of elements should be 3 times 3 times 2, which is 18. Okay. So this thing running that many times... if global... Oh, this is probably wrong. If global ID is greater than kernel size, right? Yeah, our outputs is kernel size, not image size. Okay, so that should help, at least a little bit. So then we won't... Okay, so now we have 0, 0 twice, so that's a problem. But now it makes sense because it's at least 0 and 9 are supposed to run. It's that the input channel calculation is wrong now. So we get 9 here. Oh, this is percent in channels, maybe? Yeah. Input channel is 3 by 3 by 2 by 1. Yeah, so output channel is this. Yeah, and then is kernel size calculated right? Kernel channel size times input channels. Yeah, I think that's right. That seems more correct. So now, no, 9 is still mapping to 0, 9 is still mapping to input channel 0, I think. Yeah. Yeah, that seems bad. So what's going on there? So 9 mod in channels. Oh yeah, what the fuck? This should be kernel size here. Yeah. That makes more sense. There we go. So now this is starting to behave a little bit more sane. Now we are also seeing 0, 0, 2, 3, 4, 0, 0, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is looking like maybe correct now. At least in terms of these numbers here. So that's looking promising. I wonder if the 140 IQ elms would be able to find these issues. Yeah, that is probably something worth testing at some point. I've been trying ChatGPT 5 a little bit, and I will say that, like, for how much shit I've given them for being stupid idiots, it's impressed me at least a little bit. Dude, I fucking couldn't figure out what to title the video yesterday. And asked ChatGPT, I was like, do you have suggestions for a Spheriphoria video title about, whatever we did yesterday? And he's like, let me try to match your typical depressed Zoomer energy. And I'm like, what the fuck are you talking about? Why the fuck would you say that? I'm not a fucking depressed Zoomer. What the fuck? Why would you call me that? That's crazy. I was like, fuck you, man. But he did, to be fair, it wasn't that bad at usually the suggestions are like so terrible. I'm like, why did I even type this? They weren't that bad. They weren't great, but they weren't that bad. So maybe I am just a depressed Zoomer. Okay, so the question is, if all of these numbers are correct, then why the fuck is this output still fucking garbo? You know what I mean? Also, are we not supposed to be calculating, like, are we not supposed to be looking at, wait, hold on a second. Are these names backwards? No, this is, because this is running, like, the right amount of times, I think. So, conv many grad kernel. Let's just double check this again. Conv many grad kernel is running here to execute B. And then here, are we pulling B out in the test? Image grads, kernel grads, and we're printing kernel grads on CPU. Okay. So then, should we not see, like, printf assigning this from this? Global ID sum. If global ID is equal to 0. I guess maybe we just do this. So that we reduce the spam. 288. Wait, hold on. Can we double check? Maybe this is wrong. 00234. Is that what we saw in PyTorch land? I think it's not. Oopsies. Python. We did something It was this. I see. So we are not handling the fact that we're looking at the top left corner. Right, we're supposed to see 00034, not 00234. So we, in this kernel, when we are looking at the image pixel, we need to offset by which kernel index we are, right? So we need to say image x offset is the kernel width over 2 minus our x position, so maybe the other way around. Kx minus kernel width over 2, right? So if the kernel width is 3, this will truncating divide to 1. So our kernel x will be 0, and this will be offset by -1. Nice. So this is the same here for y. And then we have to do, like, our clamping shit, right? So we need to say, so maybe for, like, int... we need to do like our clamping, right? So we say image y plus image y offs. So we'll call this center y here. Yeah. So our gradient, when we look at the gradient, we're looking at the center pixel, right? So we're going you know, we applied at the corner here. We applied this kernel to get this top left pixel here, right? So this gradient uses the center of the kernel y to say how much did I contribute to the final output. And then here we need to look at this pixel in the image. So maybe we call this image grad y is the better name for this. And then we have image grad, or like in grad, or the gradient y maybe? In grad y. Boom, 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 boom. Then we have, this is like in grad x. Here, boom, boom, boom. And then we have image y here, which is image y is equal to in grad y plus image y offset. Nice. Isn't the kernel gradient basically a convolution of the input stuff with the downstream gradients? Seems like in PyTorch you just multiply the top left corner with the downstream gradients to get the top left value of the kernel gradients. The top left corner with the downstream gradients to get the top left value of gradients. Yeah, we are just trying to do that same iteration we were doing in PyTorch. But we have to do it from the perspective of one pixel in the kernel, which is just like a harder perspective to deal with, I think, right? We were only calculating in PyTorch like one of the many values, where here we're trying to calculate like all of the values for all of the kernels at once, which is just like, yeah, I think you just have to like think about it slightly differently, if that makes sense. Like, in my mind, it's always way easier to think about it. Like, writing these kernels is hard for me. I don't know why. It just feels like everything is backwards from the way my brain wants it to be, which kind of makes sense, right? You're usually saying, I have stuff, I want to look at the stuff, not like I have one thing from many stuff and I want to look at like the things related to my one thing. I don't know. It feels hard to me. Which might mean that I'm doing something fucking stupid. That's very possible. Then we like heal this thing. So we say, we take the max of 0 and min of height minus 1 and image y here. Nice. And we do the same thing with x here. X, 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 width, x. Nice. He's mad because min is ambiguous because these guys need to be ints now. Probably. He wants a types match. Little whiny bitch. And now he wants me to put semicolons? Like, come on, man. Just figure it out. Figure it out. Okay, so now we have 00034 00089. That's more correct. And the question is does this pass, does this match up now? So 2.4, 2.67. Let's look at the... So 246, 267, 285, 279, 288, 295, 297 here, 299, 300. So the first kernel is right. The second kernel is busted as fuck. But the first kernel is correct. So can we just start inspecting that guy instead? So input channel equals 1 here. What the fuck are we doing wrong? Yeah, these numbers are all just fucked up, huh? Oh, but I think actually, did we comment something else that would make that make sense? No. This should work. So it should do the exact same thing in terms of iteration from the gradients, which he is doing, right? You see him doing like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. He's going like sequentially. He is looking at the gradients correctly. It must be the image input values that he is looking at the wrong thing. So let's just take a look at that. What am I looking for here? conv.c or cl. Just add to the documentation, only works with one kernel. Perfect. Perfect. So he's looking at image index by image size. So this is all the same. This input channel thing is different though. So he's looking at my input image plus input channel times image channel size. That should be more correct. Okay, now does this match? 136, 183, 226, 116, 168, 216, 96, 153, 206. Let's fucking go, baby! Let's fucking go! This fucking matches. Hell yeah, baby. Okay, so now let's try to, like, I guess build up, like, a more complicated, like, make sure that we're getting the most complicated case. First try, yeah. But to get the other values of the kernel gradients, you just slide the downstream gradient over the input image, just like in normal convolution. So couldn't you just reuse the OpenCL kernel that does the forward convolution with the downstream grads to the convolution of the kernel that slides over the pixels? Let me think. There is something there, right? Where you're right. I see what you're saying, right? Because what I did was I took this chunk of numbers here and basically did a convolution of this with the output gradients, right? And so it's that I would construct n kernels out of this by like padding, right? So in this version, we actually padded the input to like we are like extending in ours. Theirs they don't. They kind of like shrink in the values, right? So if you're running a 3x3 kernel over a 7x7 image, you like lose 1 pixel around the border, right? But like I think this is essentially what we're doing, right? They are they are basically running this kernel over the gradients and then this kernel over the gradients, right? You kind of have like 9 5x5 kernels that you could extract from this thing. And I just don't know if that's easier than doing what we did. But I like kind of get what you're saying. I think that you're right. You could formulate the problem this way and it would work. I'm just not sure if like extracting those kernels is easy or hard. But I think you're right. Okay, so let's go back to our math executor here, and let's just bring back level 2 of this thing. No, the gradients of the kernel that runs over the input. Oh, yeah, true. True, it's just the other way. Yeah, you're right, you're right, you're right. You only have one kernel that doesn't change. That does seem kind of true. Yeah, you're right. There is definitely something there. So you say, where is the center of the input I'm running over? You still have to like sign extend, which I think comes for free. Yeah, I think you're right. I think you're right. I'm gonna write this down and not do it yet, but I think you are right, and I should try that later. Because yeah, that does just seem correct. Fix me. This whole thing can probably done by using the gradients. Yeah, as a kernel that is run over the input image. Yeah, I do think you're right. Okay. Let's bring back this like 2-channel output thing. So let's just get the downstream gradients to kind of work the same here. So image GPU, kernel GPU, this is 3x3x2x2 now, which means that the output is 2-channel. And can we look at testpy and do something similar? So here we now have this. Like this, bing, bang, boom. Then this guy is reshaped to 2x2x3x3. Okay. Then we do our convolution. And this out to, this must be A range 50 now instead of, because this is 2-channel output now, I think. And then everything else just kind of works. Yeah, here we go. Nice. Okay, so can we check that we got the same outputs here for our kernels stuff? Where is this living? Math executor. So 25, 26, 27, 28, 29. Surely there's like a better way to do this, right? Even if it's just like copying this. There we go. Okay. Does this match up? So looks like up to the 206 we're good. But then the second set is fucked again. Okay, so we have convcl. We have, it must be this output channel use. It must be. You can do 5 plus control A and Vim to increase the number of 5, then repeat on each number. Yeah, that makes sense. That makes sense. Okay, can we do some more logging? in image. Let's just do this. And we'll do this if output channel is equal to 1. And this should give us some information. Oh. Okay. Interesting. So that's just never happening. Output channel does seem to be 2 here. So we pass the kernel GPU into this guy. We should be seeing... What is this? This is big Brad Dims here. We should be seeing like 3 by 3 by 2 by 2. Okay, so that's good. So then here we should be seeing output channels is 2. So we should be running this for 3 by 3 by 2 by 2, which is 9, 18, 36. We should be seeing 36 runs of this kernel. Where is this? Conv.cl. So G is this, output channel is this. So this is global ID and output channel. Okay, so we are seeing 18 runs of this, not 36. Sorry, 36, right? 3 times 3 times 2 times 2 should be 36. So the fact that this is only running 18 times seems fucking wrong. Probably our output filter here is wrong here. We're doing kernel size times n, where n is the number of images. So if global ID is greater than, this should be outc here. Cool. Cool, cool, cool. So now does this match up? Okay, we're looking for 1, 2, like what the fuck? 206, here we go. So this is 646, 742, 835, 754, 813, 870, 847, 874, 900, 361, 508, 651. I think this is right. 341, 493, 641, 321, 478, 631. Okay, hell yeah. Hell yeah, we're there. We are so back, baby. Okay. So, math executor here. We can now copy paste our expected, right? So, we just do this. Const expected kernel grads is this. And I don't know, we'll fucking something like this. There we go. Boom, boom. There we go. There we go, baby. And so now we can just go like for KG CPU expected kernel grads. We do a little test here. Hype. Hype, 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 hype. This is conv 2D, right? How similar is conv 1D? Isn't conv 1D just the same as conv 2D, but just with a height of 1? I would think they're the same. I would think. Okay, so we only have tested one of the outputs here, though. The other output is the image gradients. So we can throw that in the PyTorch test as well. So here, just instead of output gradients here, we can look at, or sorry, kernel gradients. We can look at image gradients here. And so we just need like image retain grad here to show that. And I think I need to write down this, or else I will get confused. So it's this. And then here we just have to take out the center. So this should be 1 to 1 to 6, 1 to 6, I think. He doesn't like that. Index 1 is out of bounds for dimension 0 with size 1. Oh yeah, sorry. This should be 0 to 2 like this. Or I guess we do everything 1 to 6, 1 to 6 to extract like the middle section. Cool. I think retain grad is what you need to do to train your data to make the network hallucinate. Yeah, you like make it like backprop all the way to the images. Yeah. And use that, like optimize those instead. Can we print out? We have image grad, CPU, image grads. Can we just like print out? Are these already right? They might be. They probably aren't, but they might be. We could dream. Sorry, convcl here. Where are we? Are we printing somewhere that we're not supposed to be? Yeah, fuck that shit. Okay, so this is not matching. So I guess we need to figure out, again, what is the math that gets one of the numbers here? So how is this calculated again? We have, I guess we can leave this. So this image, in this image, we have a pixel here, and he contributes to, you know, all of these runs of the kernel. Right? So we're kind of summing all of the kernels that ever touch our pixel. Yes. And we want to know, so we look at like an offset in the, if we're looking at like the kernel that runs on the top left, our pixel is here in the output, the gradient that we affect is like all of these gradients, right? So that makes sense. And I wonder if we can formulate this problem as an image kernel like Christoph was suggesting earlier, right? That seems possible. So we could do something like, I think you have to invert the kernel, right? So like, there is something where the shape of this kernel is definitely the same, right? But our effect, so we are running this kernel to get this gradient, right? So the thing from our perspective that is up and to the right is affected by the number that was in the bottom left of the kernel, right? So any change in our pixel value will be multiplied by the value that was in the bottom left of the kernel. So we need to invert the kernel, flip it over the is it like flip over diagonal? No. It's like flip horizontally and flip vertically. Yeah. Yeah. So it's just you just invert the index. So can we prove that in can we prove that here somehow? And then what about like the sign extension at the end? In the corner, do we like if we extend the gradients like this, is that a problem? I think so. I think what we're actually supposed to do is pad with zeros around the side, so that the sums for everything in the corners that aren't like these guys don't contribute or something. I need to draw the picture again. So we have some downstream gradient. We want to know in our input image how much does a change in this pixel value affect the output, and it is that he doesn't affect jack shit. Like anything outside is 0. Yeah, these things like have no effect because the kernel, the downstream, like there are no gradients out here. So we take our gradients, we pad them with zeros, and run a forward pass like a convolution of the mirrored thing. Let's try that in Python land before we implement in OpenCL land and see if that does the right thing. I think it does. I think it does. So mirrored kernels here. I'm just gonna do it by hand because I'm too fucking stupid to do it with PyTorch. So it's kind of just lucky for us, you know. This is the same. And how do we like? Can we like pad torch pad tensor? The padding size, the dimension of the input. So if we do like a print torch and then functional pad of the out grad with, I assume pad is padding left, padding right to pad the last 2 dimensions of the input. I don't understand. Is there an example? Pad last dimension by 1 on each side. Pad last dimension by 1, 1, and second to last by 2, 2. Got it. Is this not it? Oh, is it supposed to be 1, 1, 1, 1 with constant? Yeah. So pad left by 1, right by 1, top and bottom by 1 with constant zeros. Here we go. So now we have zeros padded around the outside, which is really good for us. And so now we should be able to run like padded is this, padded grad. We should be able to do a conv2d of our mirrored kernel over padded grad. And this is like hand calculated image grad. And can we print out like image grad and calculated image grad? Are these the same? If they are, we kind of get it. Fuck! Weight should have at least 3 dimensions. Oh, we need to reshape. Not bad. Oh, hell yeah. So this is the same. So we calculated this by hand by doing a convolution of the mirrored kernel over the 0 padded tensor, gradient tensor. And so this is very close to being what we want. It's just that like our forward pass padding now needs to have, we need to like support a padding method, I think. But good eye on saying that this is just the same as the forward pass. So I think that we can basically just say this conv many function is going to be conv many inner for now. Oh, sorry. This is going to be conv many calls conv many inner. And he's literally just going to like pass all the same fucking parameters, but with a padding mode. Enum padding, like padding mode extend or something, because that's what we were expecting before. And then we can call this conv many inner with padding mode here. Right? And then we just have to like write that thing. So enum padding mode has padding mode extend and a 0. Right? And then what we have to do is use that somehow. So this like clamping shit now has to be done. I guess it's like we need like a sample float sample image pointer, or like sample image channel start. I wonder if you can just do like this, x y with the padding mode, right? And here we say like if x is less than 0, we probably need like width and height as well. Which makes me think we should have like a image sample, like channel sampler or something, but that's fine. We'll just do lots of parameters for now. If x is less, okay, I guess we like switch on the mode here. And if we have like a padding mode extend, it's like y is equal to this. X is equal to this. And then we return channel start plus y times width plus w. That sounds kind of right. Uh-huh. Does this stuff need to be, like, in these braces? Why is it mad? Like, why is this stuff not highlighted correctly? Oh, we missed H. And then we don't need to cast this anymore. Okay. Sure. And then we have padding mode 0. And I guess this actually, it comes down here. And here we say, if x is less than 0, or x is greater than or equal to width, or y is less than 0, or y is greater than or equal to height, we return 0. And then here we can say, like, image val is sample image channel from in image channel here, image x, image y, width, height, padding mode, right? Which means we don't need in image row anymore here. And then does in image channel here need to be annotated with like global? Yeah, well, this thing needs to be global here. Uint expected expression? What the fuck? Oh, here. True, huh? Find this, go back by one, go to the first character and delete. Pipe. Okay, so does everything else, does the existing stuff still work? Looks like yes. So now we should be able to, for conv many grad image, we call, so we have to flip the kernel, which means that like this inner function also needs a like indexing, like kernel indexing mode, right? Kernel index mode normal, and then we have mirrored as well, right? And then somewhere, how do you record macros usually? Whenever I try to record macros, like my brain forgets how to type. I think I just like, it's like how I know how to say words when I want to make a sentence. I just like have grammar that I like understand how to use, and it's like I remember it. I don't know. I guess I'm lucky. So here, I guess it's like the same thing. Down here, the kernel value, it's like sample kernel val. Probably. Given the kernel and kernel x and kernel y and kernel width and kernel height with the kernel index mode here. And you know what sucks here though? I bet you this is like fucking slow. Unless the compiler is pretty smart. We're like moving a lot of like if statements into like the innermost loop, which is like kinda shit. It might actually be better to just write these different functions, which is like bullshit. But like whatever. That's for later. Maybe it's fine as well, right? We don't know yet. Okay, so if it's normal, I think we just break. Nothing to do here. And if it's mirrored, it's like we do like kx is equal to k width minus 1 minus kx. So if kx is 0, we get the right side now, and then ky is the height minus 1 minus ky. I think that's right. And then we just return kernel at kernel, like at ky times kernel width plus kx. Sure. Just call this image kernel because overloading the word. And then here we can call sample kernel val from, I guess, kernel channel. Kx, ky, k width, k height. You said plus and type star. Yeah, that sounds possible. Let's see. Yeah, I did do that, huh? Good eye. Good eye. Okay. So we just want to make sure that everything here still works. Cool, everyone's still happy. And so now we have kernel index mode here that gets pulled up from enum kernel index mode, kernel index mode. Now the default thing calls kernel index mode normal, and we should be able to like flip that shit now in our thing, right? So what did we say? So we're just literally gonna like conv many inner. Okay, so our input buffer, we're doing a convolution on the gradients, right? I think is what we said. And the kernel is just our kernel. Our output is just our output. Okay. Width, height, in channels. Is in channels different now? In channels, I believe, is now out channels. Because because we're oh, but then wait, then how does the kernel work? Oh, does that mean we need to flip output and input channels on the kernel? How did this work? How the fuck did this work before? Because isn't our output gradients, it's 2-channel, right? Oh, it just happens to be that our 2 channels are like the same. We did 2 by 2. So it just happened that the shapes match out. If every thread takes the same path, the ifs are fine since no threads will be waiting idle. Yeah, but it's not great because you have like, I guess like you're relying on the branch predictor to kind of like go the right way. I think ifs and loops are bad typically. It can't like SIMD it out, which I think is still a thing that GPUs will do. You know what I mean? Like the compiler can't make as intelligent guesses. Yeah, I think that we have to flip our output and input channels. I don't want to reuse this fucking code anymore. I don't like this. Because you know what we could do instead, though? Is if we mirror the kernel first and just do the forwards pass, if we do the kernel mirroring outside, then it's okay. Yeah. So let's do that. Let's we can still keep the padding mode change. I'm okay with that. But let's like get this kernel mirror mode thing out. And we will do the kernel reshape, like the kernel mirroring, externally. So if we have a kernel that's like like make grad kernel. Make, yeah, something like this. And he takes in like in kernel, grad kernel, or like make grad mirrored kernel. Yeah. This is getting close. So then we pass in like the dimensions of this input kernel. Right? Oopsies. This is like this. Then we can just kind of do this, right? So we can say I guess like n is k width times k height times in C times out C if global ID is greater than or equal to n, we return uint global ID is get global ID 0. Yep. Okay, that's looking pretty hype. So we just go like, this is running for output, I guess. So I guess we have like in out x is global ID over percent height. Out y is, we have like channel size is k width times k height. We got kernel size, or like yeah, I guess this is times in C or something. Yeah. Cool. Cool. So then we can start getting crazy. So we say global ID percent channel size over kernel height, I believe is right here. Out channel. Oh, that's confusing. Can we just do this? Throw some nums in here. There we go. Out in C and out C. Confusing. But does someone still have some preprocessor that you can leverage for some of this code reuse? Yeah, I think there probably is, but I don't really know what I'm reusing yet. What I usually do is I like start with by doing like the re-implement thing and then figure out the commonalities later. Because like I'm not really like sure what I want to reuse yet, if that makes sense. Okay, so it's probably something like this. Probably something like this. And so our in x is, it's like, whoa. Yeah. Yeah, I guess that's right. In x is kernel width minus 1 minus out x, right? Our in y is kernel height minus 1 minus out y. Our in channel is out in out channel is out channel, and in channel is, I think we're flipping out and in, right? Amazing variable names. Hell yeah. Is that right? So because we want to flip the inputs and output channels, and we want to flip the we want to mirror X and Y. So I think that's right. I think. So just grad kernel at global ID is equal to in kernel at some shit. So in out channel times kernel size plus in channel times channel size plus in y times kernel width plus in x. I think that's right. Yeah, that sounds right. Yeah. Yeah. So now we just have to call this and make it, but then we can call conv many grad image instead of the in kernel buff. We'll call this grad kernel buff. And now this should allow us to just like replace this whole thing with this call to conv many inner. Yes. This is like the generic version of this thing. So just, we're doing again like a backwards convolution. So we're running it on the gradients in grad buff. The kernel buff is our grad kernel buff, okay? Our output buffer is our out grad, okay? Width, height, in channel is now out channel because we're going backwards. N should be the same. Kernel width, kernel height are the same, but the kernel, we're going backwards again, so this out channels is in channels here. And then the padding mode is padding mode 0. Woo! That's a maybe, dude. That could work. That could work. So can we now, in our CPU side, where the fuck are we? Where the fuck are we? Math executor. So when we do conv many grad, we have to we do like a mirrored kernel equals self conv many mirror kernel. What do we call it? Make grad mirrored kernel. Conv many make grad mirrored kernel. Is this for the barcode scanner? Yeah. I mean, by some metric of 4. Yeah. So we're gonna like execute this kernel with something. I don't know what yet. Why do you have random files just named a square bracket and a semicolon? It's because like I accidentally like missed the enter key, right? So I might do like, instead of doing :W enter to save, I might do like : enter W and then like slap the square bracket by mistake, or like the semicolon because I'm a dumbass. You know, there's like, I just accidentally hit the button sometimes. It's for the barcode reader the same way that making a trellis out of wood is for making wine. Yeah, I agree with that. Okay, so we need this guy. Conv program, create kernel. Make grad mirrored kernel. And then we do this, and we slap that down here. And then we save this thing here for later. And then wherever the fuck we're trying to use this thing. Okay, so kernel num elms is kernel input dims num elms. We put that shit here. This is how many times we're running this thing. And then we have to throw some inputs on this. So, bum, 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 bum. All right. So it's buff is in our kernel input like this. We got the second thing is the grad kernel here, which we don't have. So grad kernel is equal to try create tensor uninitialized with dimensions of, I guess technically we can lie here. We could just like do a clone of the other dims, but let's just do it correctly anyways. So the width and height of this are the same, but the channels have flipped. Okay? Then we can do width. We have in num channels and out num channels, but like for who? You know? So my out in channel is this over channel size. It seems to shockingly kernel. Oh, so this is kernel size here is for the input or the output. So this has to be like this. We want out kernel size, right? So this is in out number of channels. And then here, it's actually, we need out kernel size and in kernel size as well, because these are different. Yeah. There we go. That's funny. That's crazy. Dude, how fucking confusing. We might have to test this function explicitly, because I think that I'm going to, like, my brain is going to fucking hurt. He's going crazy from all the kernels and tensors. I'm actually, like, gonna lose my fucking mind. Okay. So, kernel width, this is great. We still have, kernel input dims get 0 here. I think it's 0, 1, 2, 3, right? Just boom, 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 boom. Like, there's a very good chance this is fucking wrong. So what we should do here, actually, for our test, is we need to make sure that our kernels are different. Right? We have duplicated kernels here in our test. So I think what we actually need to do is just do like 2s here. Oh, no, wait. It's fine? No, it's not fine. This is important. I don't really know how yet, but it seems relevant. Seems relevant in some way. So can we check what the mirrored kernel of this looks like? Just temporarily. God, I wish C++ would adopt something like that error prop operator. Yeah, it's pretty hype. In out numc and in numc is what finally did them. Yeah. Okay, so can we look at the gradient kernel that we got out of this? To CPU. Grad kernel. And can we just print this thing? Flipped kernel is this. What's bothering me though is I don't even really know what this thing is supposed to fucking look like. Flipped kernel. So we got, this is the first kernel. He has been moved from -1 on top to 1 on bottom, I think. Yup. So he's been flipped. Then the second kernel. The second kernel is actually the flipped version of, I'm hoping flipped version of this. So here we should see 000, then horizontal flip 000. Yeah, so this does look like they've kind of swizzled. It looks like they're going flip this, then flip this. Right, so that makes sense because we want channel 1 to be next to each other and then channel 2 to be next to each other. So I think that's kind of right. I think that's kind of right. Maybe write a test for just the mirror function. Should be a simple test to write. Yeah. It's probably worth doing, right? I mean, but if I've just manually checked it, then like we kind of get the test for free by testing the rest, right? So like I think it's correct. So for now, I think I'm just gonna leave it. Okay, so now when we call conv many grad kernel, kill me. Conv many grad kernel, now we want downstream gradients. Why the fuck was this image input before? We want grad kernel buff here. Famous last words, yeah, so true. B grad, then this is all input space, so I think this is all correct still, because we do the flipping here, out C, in C. There's a chance? There's a non-zero chance that this is correct. I don't like... Oh, this is the wrong fucking thing. We're trying to do image kernel, not kernel kernel. Of course. Of course. How silly of me. How silly of me. We are supposed to be using this thing in the other function. God fucking damn it. Okay. Conv mini grad image kernel, not kernel kernel. Dumbass. And then this is grad input now. And then that makes more sense just overall. Okay. So now does this match this in any way, shape, or form? No. Kill me. I'm confused again. So when we did our mirrored kernel in test pi. We need to do 2s here. I'm a dumbass. Okay. So this is throw some 2s here and here is what we did in our version, I think. -2s and 2s, yep. And then here, when we flip, we want to do keep channel 1 together and keep channel 2 together. Okay. So I think this is the mirrored version now. Okay. let's make sure that our mirrored gradients match up. So we did calculate this right in the Python version now. Okay. So now the question is did we calculate this right? No. We did not. So we have to start looking at why the fuck that is. Ow! My stupid little brain, man. Okay, so the good news is I'm pretty damn sure the kernel mirroring is correct. Pretty damn sure. Let's just double check that one more time just for peace of mind. So 0, 1 on top, -1 on bottom, 2 on left, -2 on right. 1 on top, 1 on bottom, 2 on left, -2 on right. Okay. Then 1 on top, -1 on bottom. Whoa. Oh, sorry. 1 on left, -1 on right, 2 on top, -2 on bottom. 1 on left, -1 on right, 2 on top, 2 on bottom. Okay, so this is the same. The mirroring is correct. Hand wavy. Hand wavy. Then the question is how did we fuck up conv minigrad image kernel? I guess we just have to start logging convolutions. The padding mode is the most suspect thing, right? However, that seems pretty hard to get wrong. If padding mode is equal to padding mode 0, we can do some logging here. So we can say we have global ID this thing, and we have f times f. Let's just start there. Global ID like this. This will start giving us some information. I think we also need kernel X and kernel Y. What are we calculating here? I don't know, man, but okay, so we are... Jeez, there's just so many fucking numbers. So good news here is the top left corner seems to be sampling... What am I looking at here? How does G, like, relate to everything else here? We are iterating for each pixel in the input. Each pixel in the input is what we're looking at. So we're looking at, like... Okay, let's actually do image and kernel index here. So, like, kernel center, I guess we'll call this, is at some location. This is at image CX and image CY. Okay. Cool. Whoa. Why is this mad? Uint? Uint. Oh, global ID is not in here anymore. My bad. My bad. Okay, so when we are at 0, 0, so for the whole first row, we get zeros everywhere. Zero times zero seems confusing to me. Then for the first row, we get 5 times 0. Oh, sure. So what are our two values that we're logging here? It's the value from the image and the value from the kernel. So the kernel value here. Oh, we definitely see some like crazy values down there. So something's wrong with like indexing, maybe. But here we have, can we only look at one channel or something? Just to like help my brain. Okay, so kernel 0, 0 should always be 0, right? So that makes sense. The first row in the image is all zeros, which is good. Then the gradients for the second row in the image are 0, 5, 5, 5, 5. Oh, wait, hold on. Are my gradients wrong compared to the test script now? They might be. Can we just double check that that our gradients are correct? So it's out.grad. I think they should still be the same, but I think I just want to be sure. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, okay, so this is good. Which this matches our test, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, cool. Cool. Then why in our thing are we seeing? Hold on. There's something that looks concerning about like 5, 5, 5, 5, 5, 0, 10, 10, 10, 10, 10, 0, 15, 15, 15, 15, 15, 0. This seems concerning to me. So like this is when we are at x1, y1, x2, y2, x3, y, or sorry, x0, y1, x1, y1, x2, y2, x3, y2. We're seeing 5s everywhere? Which seems bad to me? Like, we're only seeing, like, multiples of 5. Which indicates to me that we're only ever seeing this leftmost column, right? It looks to me like the downstream gradients are not coming from the right place here anymore. Okay, what happens, hear me out, if we switch the padding mode here? No, that's... How the fuck was anything else working with this so wrong? We were doing plus W here instead of plus X? Nothing should have worked there. So the fact that the other tests were still passing is like very concerning. But now is this right now? 57, negative 10, negative 11, negative 12, 47, negative 72, negative 14, negative 14, negative 14, 56, negative 82. This is looking pretty good. What about from the backside? 111, 84, 82, 80, 59. I think it's right. I think it's right. So we just had a little bug here where we were adding the width instead of the X value. Oopies. I'm very concerned that that wasn't showing up in other tests we were doing, though. That seems really fucking bad. Yeah, that's shocking that that was working, actually. Oh, because we weren't running the other tests. We were only testing conv many grad. We were not running the test conv many. So, like, of course it could be broken. My bad, my bad, my bad. Okay. At least everything makes sense now. So now I guess we just have to update the expected. So we should have, like, expected image grads here. Which we can copy paste from our test script, right? Hell yeah. Okay. I don't know, man. Um, delete this shit. Okay. Hell yeah, dude. Expected image grads. And then here we should also probably check their shapes, right? Expect kernel grads dims are equal to oh, we are checking the dims there. Okay, we're chilling. We're chilling. So can we turn off the test filters now? Let's take a look. If you don't run it, you run the unit test, they can't fail. Huge strategy. Yeah, thank you, thank you. We're geniuses around here. Holy fuck, man. I did not expect this part to take this long. But we fucking got there, baby! Let's go! So we can now theoretically backprop a kernel. Or a convolution. We're at 157, so I was kind of hoping that this would be like the first like 15 minutes, and then we would actually do the like convolutional neural network part for the rest of the stream. But I guess, you know what, this is kind of like a nice little ending point. And we can do the actual convolution part tomorrow. I'll probably do a little bit of like off-stream cleanup here. I do want to take a look. I think that Christoph was right, and I should update this other the other gradient function, the kernel grad function. There's like something there where we can reuse conv many inner there as well. But tomorrow we should be able to hit the ground running on actually trying to train a neural network, which will be exciting. And we'll probably run into all sorts of problems there too. So I think we call it there. Thanks for watching, guys. If you like what you saw, we stream most days 12:30 Pacific time. We aim to end around 3 or 4. It is about 3 now. So anywhere from 2.5 hours ago to an hour from now is when you should expect to see us live. We're working on this neural network training thing, but there's a lot of other cool stuff in the YouTube backlog if you want to check that out. There's a YouTube link in the Twitch description. Some stuff goes there, some stuff does not. The metric is essentially if it's something that I think the YouTube algorithm will promote, which, you know, is not necessarily this it's not the same as the set of things which I think are interesting. So the other stuff, you know, like cleanup, unit testing, research, just kind of like things that aren't like a nice packaged thing, but is like still me working on this stuff. That stuff goes on Patreon or on YouTube members or in the Twitch VODs. We do that so that we have something to give people who want to support the stream. The stream will stop happening when I run out of money. So if you want to see the stream continue and you want access to VODs of the stuff that doesn't go up, you know, drop a Twitch Prime or subscribe on Patreon or YouTube. Cool. I think that's all the plugging we got to do. YouTube, peace out, and Twitch, let's find someone to raid.